Okay, welcome all of you. In the last class, I started introducing about the internal interaction parameters. We discussed 4 different types of internal interaction parameters: chemical shifts, scalar couplings, dipolar couplings, and for the nuclear spins greater than half, it is also we also have quadrupolar interactions. And we are dealing with spin half nuclei. Quadrupolar coupling we do not have to consider. Also there was a minute difference I told you. All other interactions are magnetic interactions except quadrupolar interaction, which is electric interaction. Since we are dealing with spin half nuclei, we do not have to worry about quadrupolar interaction. Further, these internal interactions, if you have to worry about it, if you consider in the solution state, dipolar coupling we can average it, we can remove it because that gets averaged out. Every interaction parameter in NMR is anisotropic, and in the solution state all the anisotropic interactions get averaged out. We do not have to worry about it, and what we are going to be dealing with is only our isotropic chemical shifts and J couplings, scalar couplings. We did not discuss scalar coupling, we will come to that later. But in the chemical shifts, I said how it comes when you put the sample in a magnetic field, because the current induced by the external magnetic field, the circulating current in turn induces magnetic field. And I said induced magnetic field is very small. The external magnetic field is of the order of several Tesla, but the induced magnetic field is 0.4 or 5 zeros at some value. It is a very small negligible value, but it adds to the external magnetic field. The field seen by the nucleus is not just the external magnetic field, but also the field induced by the nuclear spins due to surrounding electrons at the site of the nuclear spins by the surrounding electrons. As a consequence, there is a shift in the resonant position. The resonance frequency is not just 400 megahertz, 400 megahertz plus some value, and this causes a shift in the resonance position, which we call it as chemical shifts. And we took the example of a hypothetical molecule, different functional groups that have different charge distributions. As a, for example, if you take CH bond, it is elliptical. For any other bond like OH or something, some other bonds, charge distribution is having different shapes. As a consequence, the field induced at the site of the nucleus is different. So in any given molecule, different types of at the different sites of the nucleus, if the charge distributions are different, then we are going to get different peaks in NMR. That is what we understood. And I also said the nuclear spins do not get involved in chemical reactions, but they give information about the chemistry of the molecules, because the electronic charge distribution at the different nuclear sites are different. They give rise to different peaks in NMR. If you analyze and interpret, we can get about the chemistry of the molecules. You can understand the chemistry of the molecule. So this is a very important thing. So this is what we understood. Today we will try to go further and see how different electron densities affect the chemical shifts. That is what we will discuss today. For example, I consider a methyl group, methane group, CH group. Let us see how the electron density will be there at the site of the nucleus. Methane group has a single proton, only one proton. Hypothetically, we have written the charge distribution at the site is like this, and effective field seen by the nucleus is more than the static magnetic field. So B effect is more than B naught. It is not same because shielded by one of the protons, electrons surrounding that. Go to methyl group, there are 3 protons, electron density due to 3 equivalent protons there, that is much different now. The effective field seen by the nucleus is more than the static field here, B effective is more than B naught. But remember, I am considering CH proton here and CH3 proton here. Methyl group has 3 protons, CH3. So, each of them has different effective fields. Effective field for CH proton is different more than that of B naught. Effective field of methyl proton B effective is more than that of B naught. But between these two, B effective of the methyl is more than B naught of B effective of methane. Why? Because these are 3 protons, B methane group has only, B effective has only one due to one proton. So, B effective of the methyl proton is more than the B effective of the methane protons. So, but that means methyl protons are more shielded than methane protons. Understand the concept. If I consider the methane proton, it is shielded, more shielded than B naught. Methyl proton is more shielded than B naught. Effective field between these two are different, but when you compare methane proton with the methyl protons are more shielded than methane proton, because B effective of methyl is more than that of the methane protons. So, as a consequence, effective field seen by the methyl proton is more than the methane proton. That means it is more shielded. The field seen by this nucleus is much more. So, as a consequence, CH3 protons resonate at higher field than CH proton. Because of 3 protons, shielding is more, it comes at higher field. So, shielding also depends upon number of equivalent protons. Now, consider the example, instead of only this and this, methane and methyl, we also bring in CH2 proton, methyl, methane and CH2 also, all the 3. Now, the charge density at the site is different here. There is only one proton, we have written charge distribution some shape. Here for 2 protons it is slightly different, but more than this. Here for 3 protons it is different, but more than this and this. So, that means this is more shielded than this is more shielded than this, and this is more shielded than these two. As a consequence, CH3 protons is more shielded, comes at a high field region. If I consider the magnetic field direction, B naught field is plus induced field is more for this. B naught plus induced field of CH2 is here, it is less than this, but more than this. If you come to CH, it is less compared to this and this. So, there are 3 peaks, one more shielded comes at high here to the right side, because I am increasing the magnetic field direction from left to right, that is the convention in NMR. Field always increases when you go from left to right. So, more shielded comes to the right, then CH2 less shielded, then CH which is less shielded than these two. This is how the NMR spectrum comes. For if I have 3 functional groups, only we have 3 groups, 3 peaks, CH3 one which comes at the high field is more shielded CH3 with 3 protons, then next to that is CH2, then next to that is CH. You understood? This is how we see the peaks in NMR. Just to give you the comparison, if you look at the bell analogy, fantastic, in one of the temples, a beautiful bell analogy we could see. They have put 3 different bells. Look at this bell, this is the nucleus. Charge distribution, I consider this bell, at the center is this nucleus, this is a charge distribution, this is much larger, 3 protons, shielding is more. Come to this CH2, this smaller bell, this is the nucleus and charge distribution is much smaller than this. Go to this bell, even smaller than this, charge distribution, this is the nucleus, is much smaller than these two. Fantastic analogy, is a bell analogy where shielding, because of the different charge distribution of 3 protons and 2 protons and 1 proton for methyl, methane and methane group are different. So, now we will go further. We consider only CH, CH2 and CH3. What happens in a given molecule, it is not only these type of protons, we have different functional groups. It could be OH, it could be OCH3, it could be CH3, does not matter. So, we saw that CH3 we saw it comes from the high field. Let us consider a methoxy group. For CH3 add a oxygen group, it becomes methoxy. Now oxygen you see is an electron withdrawing group, it is an electronegative group. So, it deshields the CH3 to some extent. Instead of coming here, it comes to the left side. From high field it moves to the low field side. I said low field to high field you go from left to right. So, instead of coming to the right it moves slightly to the left because of OCH3 addition of oxygen. That means oxygen OCH3 group is deshielded compared to CH3. Let us go to OH group. This is the OH group, very single proton, but directly attached to oxygen. It deshields, it withdraws electrons from this, more deshielded. When you have withdrawing more and more electrons, more and more get deshielded. So, what will going to happen is when it is deshielded, it comes even more low field compared to CH3, OCH3, OH is here. This is a hypothetical graph I am giving you. Of course, in a given molecule, OH may be surrounded by something else, it may come here, OH can go anywhere in the spectrum. I am just giving you comparing between these three. Okay. When compared to OCH3 and CH3, OH is coming to the downfield, that is low field, that is what I am telling you, that is the concept I wanted to tell you. Okay. With this, I will introduce a term called chemical equivalence, because in a given molecule you may have a symmetry. Because of symmetry there will be chemical equivalence. When you have chemical equivalence you will not get number of peaks. Chemical equivalence brings, and because of this symmetry brings down the number of observable peaks in the NMR spectrum. Number of peaks gets reduced. Look at this one, all chemically equivalent nuclei which are interchangeable symmetry operations, they have the same chemical shifts. But I have not introduced the coupling, but I will introduce later. But the coupling to all other spins, that means the interaction of this to other spins could be different. Coupling may be same, but the chemical environment will be same. Coupling to may be different, but the chemical environment will be same. They are called chemically equivalent spins. They are interchangeable by symmetry operation. And remember, in the NMR only chemically equivalent spins, only chemically equivalent nuclei give distinct peaks in the NMR. If they are chemically equivalent, they will overlap and give rise to the same peak. Peak will not be different. But if they are chemically inequivalent, that means the chemical side, the charge distribution at the site of the nuclei are different, then they give rise to distinct peaks in NMR. Please understand, chemically inequivalent nuclei give distinct peaks in NMR. Now look at this bell analogy. All these bells have this identical, on the top of it you can see all of them have the same shape. Of course, when you take the photo from left or right, it appears they are different, but they are all of the same size. They are all chemically equivalent. If you take such type of molecules with a chemist, if you look at this chemical equivalence, it gives rise to a single peak in NMR. Similarly here, they give rise to a single peak because all of them are chemically equivalent. So remember, only chemically inequivalent spins gives rise to distinct peaks in NMR. Alright. Let us consider the molecule like this. What about this molecule? It is difluoroethylene. Is there a symmetry for this molecule? If I write the symmetry axis, there is a symmetry axis like this. What does it mean? Two fluorines are chemically equivalent, two protons are chemically equivalent. If I see the proton NMR, the proton 2 and 3 are identical, having the same chemical environment, the chemicals charge distribution at the site of these two protons are identical, there is no distinction. So, they give rise to a single peak. Although there are two protons, because of the same chemical environment, it gives rise to single peak. Now, if I go to the fluorine NMR, there is also possible to see fluorine resonance. Then this one, this and this 1 and 4 are identical. See, like protons, these fluorines also have same chemical environment. So, if I see fluorine NMR, this and this gives rise to single peak. For this molecule, remember, if I take proton NMR, you get single peak. If I take fluorine NMR, also you will get single peak in fluorine NMR because of chemical equivalence. Let us go to, of course, there is another parameter called coupling, which I have not, which I will introduce maybe tomorrow, next class or after subsequent classes. The coupling between proton 1 2 and 1 3 are not same. This coupling and this coupling between the fluorine are not same. Similarly, this coupling and this coupling are not same, they are different. Couplings may be different, but the chemical environment is same, chemically they are equivalent. Okay. Let us go to a molecule like this. In this molecule, then what is going to happen? Is there a symmetry for this molecule? Of course, there is a symmetry axis here. What does it mean? Same molecule, now the fluorine substitution position is different. Again, because of symmetry, remember, fluorine chemical shift of 1 and 2 is same, chemical shift of 3 and 4 is same, coupling may be different, 1 3 and 1 4 may not be same, but if I take proton NMR, these two protons gives us a single peak. If I go to fluorine NMR, these two fluorines will give us a single peak. Now, let us go to a different molecule. Again, same difluorosubstituted ethylene. Now, the symmetry axis is different. This is the symmetry axis. Again, these two fluorines are same. Fluorine 1 and fluorine 3 have this same chemical environment. Here 1 and 3 has same chemical environment, give rise to a single peak. Protons 2 and 4 has the same chemical environment and gives rise to a single peak. Again, the coupling 1 2 and 1 4 may be different, they are not same, but nevertheless, in all the three difluorosubstituted ethylenes, fluorine NMR gives single peak, proton NMR gives rise to single peak for proton because of chemical equivalence. These are all called chemically equivalent spins. Of course, couplings will be different, that we will discuss later. Consider a molecule like this, benzene. Here there are 6 protons, all the 6 protons have the same chemical environment, they are chemically equivalent. So, benzene, if you take the spectrum of benzene, proton NMR, you get single peak. What about the carbon? Look at the carbon, the chemical environment of the carbon is also same. If you say carbon 13 NMR, that also is going to give you single peak. Of course, with a decoupled everything we will see later. So, benzene gives proton NMR gives a single peak. What about the acetone? There is a symmetry axis here. 2 CH3 groups, these 3 protons of the methyl group are chemically equivalent. These 3 protons are chemically equivalent, and also these 3 protons and these 3 protons are again equivalent. So, if you take the acetone spectrum, proton NMR, you are going to get a single peak. Come to a molecule like this, we have only one CH3 group, you get a single peak. Go to cyclohexane, very interesting molecule. There are 12 protons, and interestingly, all the 12 protons are chemically equivalent. If you take the proton NMR of this, you get single peak. If you take the carbon 13 NMR of this, you will get a single peak. These are all chemically equivalent nuclei. Same if you go further, methyl acetate, these 3 protons and these 3 protons are different. This CH3 and this CH3 are not same, There is no symmetry for this molecule. Chemically they are inequivalent. As a consequence, this CH3 will gives one peak, this CH3 will give one peak. Go to paraxylene. Now there you can write a symmetry axis for this like this and this. Because of that, and this has symmetry axis 2 like this, these 3 protons of methyl and these 3 protons of methyl both are same. 2 methyl groups are identical, chemically equivalent, gives us a single peak. There are 2 methyl groups in the paraxylene, but it gives us a single peak. Go to these 4 protons. 4 protons of the phenyl group here are identical because of the symmetry operation, that gives such a single peak. So, if I take the proton NMR spectrum of xylene, these CH3 groups, 2 CH3 groups give such a single peak, 4 protons of the phenyl group gives such a single peak, only get 2 peaks in spite of the fact molecules have 2 CH3s and 4 protons, CH protons. Go to acetaldehyde, this is like this. Acetaldehyde, we have only CH3 proton and CH proton, they are different, there is no symmetry. So, acetaldehyde gives you 2 peaks, one for CH3, one for CH. So, I understood how the chemical equivalence helps in reducing the spectral complexity. More the symmetry in the molecule, more the chemical equivalence, less the number of peaks. Less the number of peaks, complexity of the spectrum is less. This helps you in easy interpretation. So, remember, chemical equivalence, if it is there in the molecule, the number of peaks that you are going to see gets drastically reduced. Let us look at this thing. See, most of the time when you are dealing with the organic molecule, invariably many of the molecules all need not be aliphatic, you come across phenyl groups present in the molecules. Let us consider the chemical equivalence in monosubstituted benzenes. I look for chlorobenzene, monochlorobenzene. Now, where is the symmetry here? There is a symmetry axis. The symmetry axis comes along this. So, as a consequence, these 2 protons are same, they give us to single peak. Worry about the multiplicity of coupling later. These 2 protons are chemically equivalent, gives us to single peak, and this is different. So, there are 3 different types of protons here, chemically inequivalent protons. This is what you are going to see if you look for the monosubstituted benzenes. Let us look for chemical equivalence in symmetrically disubstituted benzenes. Symmetrically disubstituted, it could be ortho substitution, meta substitution and ortho. Go for this para disubstituted benzene symmetrically, there is a symmetry axis here and here. As a consequence, all the 4 protons are chemically equivalent. So, if you take the para disubstituted benzene, symmetrically para disubstituted, proton NMR spectrum, you get a single peak. What about the carbon 13? Of course, that is a different question. These 4 carbons are same, but this carbon and this carbon are different. So, if you take carbon 13 NMR, you get 2 peaks, 1 peak for these 4 carbons and 2 peaks for 1 peak for these 2 carbons. Same way, of course, in the previous example here we have this carbon is different, these 2 carbons are same, these 2 carbons are same, this carbon is same. So, in a mono substituted benzene we have 4 peaks in carbon 13 NMR, 3 peaks in proton NMR. So, now we understood for para disubstituted symmetrically disubstituted benzene we have single peak for proton, of course 2 peaks for carbon. Meta disubstituted symmetrically, this is symmetry axis, these 2 protons are identical because of symmetry, they are chemically equivalent, this is different, this is different. So, how many peaks you get? For symmetrically meta disubstituted benzene we get 3 peaks. Let us look at symmetrically ortho disubstituted benzene. Now, these 2 protons are identical, these two protons are identical. These two give rise to one peak, these two gives rise to one peak. We are going to get two different peaks for symmetrically ortho disubstituted benzenes. Now asymmetrically disubstituted benzene will go same asymmetrically, not previous example of symmetrically disubstituted. If you go to asymmetrically disubstituted, take the example of a molecule like this. One is chlorine, this is bromine, there is no symmetric substitution, they are different. As a consequence, chemical environment at the site of these two protons are different and the chemical environment at these two protons are different. In the previous example, when symmetrically disubstituted para, we get single peak, but here asymmetrically disubstituted, these two protons are same, these two protons are same, we get two peaks, two chemical environments. These two protons have two different chemical environments, these two protons have chemical environments different. So, we get one peak for these two protons and one peak for these two protons. What about asymmetrically disubstituted meta disubstitution? Now, there is no symmetry at all. Where is the symmetry here? There is no symmetry. All the four protons are completely different. I have put different colors. So, this proton is different, chemically this is different, this is different, this is different. All the four protons gives rise to four different chemical shifts, they are chemically different, inequivalent. So, we get four peaks for asymmetrically disubstituted meta disubstituted benzene. What about chemically asymmetrically ortho disubstituted benzene? Very simple here also, all the four are different, there is no symmetry. So, we get four peaks for this. Very interestingly, go for this. This is symmetrically trisubstituted. Of course, this is Ca3 protons, they give us two different peaks, all of them. But look at this phenol groups here, this is different and this are different. They have different peaks, they are chemically inequivalent. This gives different peak, these two gives one peak, this gives one peak. Of course, Ca3 gives rise to, I am not worried about that, only I am worried about the phenyl group. This gives one peak, these two, and this gives one peak. What about symmetrically trisubstituted benzene like this? All the three chlorines are in the 1,3,5 trisubstituted trichloride substituted benzene. Now, you can see all the three protons are chemically equivalent. So, what will happen if I take the proton NMR spectrum of 1,3,5 trichlorobenzene? You get only single peak. There is another possibility, we can have a trisubstitution with a different substitution like this. There is no symmetry here for this, there is no symmetry. So, as a consequence, we have different peaks. Look at this one, tetra substitution, beautiful. You have a symmetry here, okay, these two are same, these two are same, these two protons are same. Look at this one, there is a possibility here, this is also tetra substitution, and now there is a symmetry axis here, this and this are same, this and this are same, and this are different now. Look at this one, we have tetra substitution, but there is these two protons are identical, and CF3 group, of course, this CF3 and this CF3 are identical. Look at the examples I have given in the phenyl substitution, depending upon the mono substitution, disubstitution, symmetrical asymmetric, trisubstitution, symmetrical asymmetric, tetra substitution, we have different chemical environments. So, as a consequence, we understood how many peaks we are going to get in mono substituted benzene, symmetrically disubstituted ortho, meta and para, symmetrically trisubstituted, how many peaks we are going to get. So, this is the beauty of this thing. So, chemical equivalence we understood. and different examples I gave you, because we come across phenyl groups in molecules. We not only we come across aliphatic groups. I took the example of acetone. I took the example of cyclohexane. I took the example of pure benzene without any substitution. All 6 protons are equivalent. So, we understood a lot about chemical equivalence. So, when we discussed with the chemical shifts today, we understood a lot about chemical equivalence. We understood what are the things which are responsible to see chemical how many peaks we are going to get for different chemical equivalence groups. I told you only chemically inequivalent groups gives rise to distinct peaks in NMR. There is a chemical equivalence, they overlap and gives rise to reduced number of peaks. If there are 2 peaks chemically equivalent, which gives rise to single peak. If there are 3 groups which are chemically inequivalent, still all of them will overlap and give rise to single peak. So, we understood what is the chemical equivalence, how the peaks will come, took the number of examples of this thing. So, we discussed lot about chemical shifts and how the chemical shift arises, how the chemical different functional groups are responsible for it. We took the example of methyl group CH3CH2CH. CH3 is more shielded than CH2. CH3 is more shielded than CH group. Then as a consequence we saw CH3 comes at high field, then CH2, then CH. Instead of CH3, if you put OCH3 and OH, OCH3 is less shielded than CH3. CH3 comes at high field region, then OCH3, then OH. So, lots of examples we took. So, summary is we understood today the chemical equivalence, how many peaks we get when there is chemical equivalence in a molecule, when it is shielded or deshielded, where the peaks come. Took the number of example of CH3, CH2, CH, OCH3, OH, NH, etc. All these groups depending upon whether it is shielded or deshielded, depending upon number of protons which are present, whether there is a symmetry is there in the molecule or not, the number of peaks we are going to get and where it comes, whether it is shielded or deshielded matters. This is what we understood. So, I am going to stop here today. So, we have understood lot about chemical equivalence, number of peaks we are going to see based on the chemical equivalence, and shielding, how many peaks we get, where it is shielded, whether it moves to the high field or low field, that is what we understood. So, with this we will stop here today. We continue further about chemical shifts, the reasons for this, how we get and everything based on the symmetry operations, how many chemical shifts are there, how many chemically equivalent groups are there, everything. We will continue further and understood the factors that affect the chemical shifts. We will discuss that in the next class. So, I am going to stop here today. Thank you very much. I hope I have given a lot of information about chemical shifts already. So, we will continue further and discuss a lot of things in the next class. So, thank you very much.